This is a video of an example of how to determine if an improper integral converges or diverges. Okay, so in this video, we're going to look at the improper integral from 0 to infinity of e to the negative x times sine x. We want to know if this integral converges or diverges. Okay, so before we do that, let's see what this integral represents. If we look at the graph of the function e to the negative x sine x for x greater or equal to 0 and less than infinity, the graph, you can use Desmos to generate this graph, or use the methods that you learned in Calculus 1, how to generate a graph. This is what the graph looks like. E to the negative x is a decreasing function, while sine x is a wave. So this will keep the wave pattern, but the wave will keep decreasing as we move to the right. And this graph encloses area. Some of the area is above the x-axis and some below, as you can see right here. And so the improper integral from 0 to infinity of e to the negative x sine x is equal to the net area enclosed by this graph and the x-axis. That means the integral from 0 to infinity of e to the negative x sine x can be said to equal to the area enclosed above the x-axis minus the area enclosed below the x-axis. So this is called the signed area. Remember, area is always positive, so this is the difference of two positive numbers. And if this integral converges, it means, and it's positive, it means there's more area above the x-axis than below. If the answer is negative, it means there's more area below the x-axis than above. You can probably guess what it will be. So the improper integral can be expressed in this limit form as the limit t approaches infinity integral from 0 to t e to the negative x times sine x dx. So first thing we need to do is find an antiderivative of e to the negative x sine x. And of course, we do that by parts. It's what's called a boomerang integral. That is, we don't do it directly. It'll come back after two iterations of integration by parts. It'll return to the original integral, and then we use algebra to evaluate it. Let u equal to e to the negative x, dv equal to sine x dx, du would be negative e to the negative x dx, v is equal to negative cosine x. So the integral, using integration by parts, the integral is going to equal to u times v, which is negative e to the negative x cosine x, minus the integral of v du. Both v and du have minuses, so they cancel or they become 1. So it will be a minus integral of e to the negative x cosine x dx. And now we want to use integration by parts on the integral on the right, that is on the integral of e to the negative x cosine x. We use the same idea. U equals e to the negative x, dv equals to cosine x dx. That means du would be minus e to the negative x dx, and v is sine x. So integral of e to the negative x cosine x equals to u times v, which is e to the negative x sine x minus the integral of v du, but that has a minus in it, so it'll be plus the integral of e to the negative x sine x. And now we're going to put the two together. We have the integral of e to the negative x sine x dx. It was negative e to the negative x cosine x minus the integral of e to the negative x cosine x, which equals to e to the negative x sine x plus the integral of e to the negative x sine x. And so now that's all we really need to evaluate the integral. Let's write this out one more time. The integral of e to the negative x sine x dx is equal to negative e to the negative x cosine x minus e to the negative x sine x minus the integral of e to the negative x sine x. Now we're going to take the integral on the right with a minus sign, move it over to the left, so it'll be plus. Two of those integrals added together gives us 2 times the integral of e to the negative x sine x dx equals to negative e to the negative x cosine x minus e to the negative x sine x. Divide both sides by 2, and we have found the antiderivative of e to the negative x sine x. It is negative 1/2 e to the negative x cosine x minus 1/2 e to the negative x sine x. And now let's return to the improper integral. Remember, it's the integral from 0 to infinity, e to the negative x sine x. We write it in the limit form as the limit t approaches positive infinity, integral from 0 to t of e to the negative x sine x. Now we have found that antiderivative, so this will be limit as t approaches infinity of negative 1/2 e to the negative x cosine x minus 1/2 e to the negative x sine x, evaluated from 0 to t. So let's plug in t and plug in 0. This will equal to negative 1/2 times the limit t approaches infinity, e to the negative t cosine t minus 1/2 e to the limit t approaches infinity, e to the negative t sine t, and then minus, let's plug 0 in, which would be negative 1/2 e to the 0 cosine of 0 minus 1/2 e to the 0 sine of 0. And let's write it out. This would be negative 1/2 limit t approaches infinity, e to the negative t cosine t minus 1/2 limit t approaches infinity, e to the negative t sine t, and then plus 1/2. All we have to do is evaluate these two limits, and we have solved the problem. So let's evaluate these two limits by using the squeeze theorem. We start out with cosine of t. We know it's between -1 and 1. Multiply this inequality by a positive value. E to the negative t is always positive, so inequality will remain the same. Multiply all three parts by e to the negative t. Now take the limit of all three parts as t approaches infinity. And the inequality is still preserved. And you can see that the left limit on the left side and the limit on the right side, t approaches infinity of e to the negative t, that is 0. So we have 0 less than or equal to limit t approaches infinity of e to the negative t cosine t, which in turn is less than or equal to 0. And that means that the limit as t approaches infinity of e to the negative t cosine t is 0 by squeeze theorem. And same thing for the other limit. We start out with sine of t. Sine of t is between 1 and minus 1. Multiply everything by e to the negative t. Inequality is preserved because e to the negative t is always positive. Take the limit of all three parts as t approaches infinity. Notice that the left limit and the right limit is 0. And we have 0 less than or equal to the limit t approaches infinity, e to the negative t sine t. And that's less than or equal to 0. And that means that the limit as t approaches infinity of e to the negative t sine t must be 0 by squeeze theorem. And so the improper integral from 0 to infinity of e to the negative x sine x is the limit as t approaches infinity of integral from 0 to t e to the negative x sine x, which is equal to minus 1/2 the limit as t approaches infinity e to the negative t cosine t minus 1/2 times the limit t approaches infinity sine t plus 1/2. The two limits are 0. We just saw that. So we have 0 plus 0 plus 1/2, which is equal to 1/2. And therefore, and so the improper integral from 0 to infinity of e to the negative x times sine x dx converges to 1/2.